Yes, welcome to this video. So this is the third video of unit number 2 of our subject PDEVC. In our first video, we have learned how to solve a homogeneous linear PDE with constant coefficients. And the right hand side function is 0. And in video number 2, we have learned how to solve a linear PDE with constant coefficients. And the right hand side function is of the form e power ax plus by, where a and b are constants. Now in this video, we'll discuss how to solve a homogeneous linear PDE with constant coefficients. And the right hand side function is either sin ax plus by or cos ax plus by. Okay, so let us explain on the whiteboard. Yes. So the topic is solving PDEs of the form partial differential equations of the form some function of d and d dash operating on z yielding either sin ax plus by or cos ax plus by, where a and b are constants. Okay, when the right hand side is either sin of ax plus by or cos of ax plus by, where a and b are fixed constants. So as usual, so the method of solving this contains 3 steps. So method is first step number 1. In step number 1, write the auxiliary equation. Write the auxiliary equation by simply replacing d with m and d dash with 1. You'll get f of m1 equal to 0. Simply wherever you find d, replace that with m, and wherever you find d dash, replace that with 1. Then we'll get f of m1 equal to 0. See, this will be either a quadratic equation m or a cubic equation m, depending on the order of this particular f of d dash. If we have third partial derivatives, dou cube z by dou x cube, or dou cube z by dou y cube, or dou cube z by dou x dou y square, like that, then it will be a cubic equation. We'll get m cube term, m square term, m term, and constant terms. If this f of d dash is only a quadratic, it contains only second order PDEs, then we will get a quadratic equation. Okay, so write the auxiliary equation. Next, solve for m, and write the complementary function. Write the complementary function as discussed earlier. Already we have discussed in video 1 and video 2 how to write the complementary function. Depending on the 3 values of m, whether they're equal or not, whether they're different, based on that we'll write. Okay. While doing problem, we'll discuss that procedure once again. So step 1 deals with only the left hand side operator f of dt dash. We will get complementary function. And the second part of the solution depends on the right hand side function. So whenever the RHS is either sin ax plus by or cos ax plus by, then the particular integral simply pi, that is nothing but the inverse operator of f of d dash, that is 1 by f of dt dash, to be applied on this either sin ax plus by or cos ax plus by. I will explain the process for sin ax plus by. The same process will be applicable even for cos ax plus b. Simply replace sin with cos. That's enough. So the procedure is same for both sin or cos. So I am writing only sin for our convenience. What will do is this f of dt dash, this will not only first derivatives, it will contain second order derivatives also. So treat this as 1 by, instead of f of dt dash, consider this as a function containing d square, dd dash, and d dash square. So treat f of dt dash as some function of d square, dd dash, and d dash square, where d square is nothing but the second order partial derivative with respect to x. D dash is nothing but the second order partial derivative, where one partial derivative is with respect to x and another with respect to y. And third one, d dash square, this is nothing but second order partial derivative with respect to y square. Okay, that means even though there are d terms and d dash terms in the are constant terms in f of d dash, treat them, keep them as it is. We will concentrate only on d square term, dd dash term, and d square term. Then the procedure is replace or put d square equal to minus of a square, not minus a whole square. Remember that minus of a square, where a is the coefficient of x and b is the coefficient of y in the given function sin x plus b. So put d square equal to minus a square, d dash equal to minus of ab, and d dash square with minus of b square. So in place of d square, wherever you find d square, replace that with minus of a square. Wherever you find d dash, replace that with minus of ab. And wherever we find d dash square, replace that with minus b square. This is the process. Then our particular integral will be this 1. Then 1 will be equal to 1 by phi of, in place of d square, we are writing minus a square. In place of d dash, we are writing minus ab. In place of d dash square, we are writing minus of b square. Okay. Of or into sin ax plus b. So this is the particular integral. But here, again, there is a problem. If the denominator is non-zero, well and good, no problem. We can stop step 2 here itself. Particular integral will be completed. But after replacing d square with minus a square, d dash with minus ab, and d dash square with minus b square, if the denominator becomes 0, then it will be failure case. So we can stop this if the denominator is not equal to 0. Whereas if the denominator equal to 0, if the denominator becomes 0, then our particular integral will become multiply outside with x, and in place of phi of d square d dash square, consider its partial derivative with respect to d by treating d and d dash as two independent variables, just like x and y. Simply ignore d dash and differentiate partially with respect to d, and then apply on sin ax plus by. Okay, understood? That means by differentiating with respect to d partially, we will denote that with phi suffix x. Differentiating partially with respect to d. So phi, when operated by dou by dou d, we'll treat that as phi x. It is to be operated on sin ax plus b. Then as per the procedure, again, replace d square with minus a square. So it will be 1 by phi x of, in place of d square, put minus a square. In place of d dash minus ab. In place of d dash square, put minus b square. And then apply on sin x plus b. This is the answer, provided same denominator is not equal to 0. After replacing in the first derivative of phi with respect to d, after replacing d square with minus a square, d dash with minus ab, and d dash square with minus b square, if we get a non-zero answer to the denominator, that will be our particular integral. Again, in case if denominator becomes 0, then repeat the same process. That means multiply with another x square, and in place of denominator, write its second derivative with respect to d partially. Find dou square by dou d square of phi of d square d dash square, and then apply on sin ax plus b. Okay, this is the process. So again, put d square equal to minus a square and so on. Okay, then put d square equal to minus a square. Same process, d dash equal to minus ab, and d dash square equal to minus b square. Then our particular integral becomes x square into 1 by, for second derivative with respect to x, we will denote with phi xx. So in place of d square, we will get minus a square. In place of d dash, we will get minus ab. In place of d dash square, we will get minus b square. And then we will multiply with sin ax plus b, provided denominator not equal to 0. So like this, since we will be given only third order linear PDEs, by this step, maximum denominator will be non-zero. So we need not discuss other steps. Automatically, after reaching this stage, the denominator will be non-zero automatically. So you need not worry. So this is the process. So, and then the last step is the complete solution is given by z equal to CF, which we have obtained in step number 1, complementary function, and then PI, which we have learned in step number 2. Okay. In step number 1, we already calculated complementary function by taking that f of d dash LHS operator only. And in step number 2, we have calculated the particular integral by taking the right hand side function sin x plus b or cos x plus b, whichever is given. Okay. Then in the last step, we'll declare the complete solution as the dependent z equal to CF of step 1 plus PI, particular integral of step number 2. This is the process. So to understand this process, we will do two problems. Okay. Problem number 1. Solve dou square z by dou x square minus dou square z by dou x dou y, dou square z dou x dou y equal to cos x into cos 2y. Cos x into cos 2y. This is the question. Okay. Dou square z by dou x square minus dou square z by dou x dou y equal to cos x into cos 2y. This is the problem. So observe the right hand side function. This is not 0. So model number 1, video number 1 concept is not applicable. This is not an exponential function. So model number 2, video number 2 method is also not applicable. But we have, instead of one sine function or one cosine function, a product of two cosine functions. But with the knowledge of trigonometry, we can express product of two sines or two cosines, or product of one sine and one cosine as sum of sines and cosines. So with that, we can express this cos s cos 2 as sum of two cosines. And then we can apply this model. Okay. So using our standard notation. So in our notation form, we are using capital D for dou by dou x and capital D dash for dou by dou y. Using that notation, in notation, the given PDE is same as the given PDE is dou square by dou x square means capital D square. So capital D square of z minus dou by dou x of dou by dou y means d dash of z equal to cos x cos 2y. Cos x cos 2y. Now, I will use this. We know that 2 cos A cos B, as per the knowledge of trigonometry, which you learned at intermediate level, 2 cos A cos B is cos A plus B plus cos A minus B. 2 cos A cos B is cos A plus B plus cos A minus B. Therefore, in place of A, if you take x, and in place of B, if you take 2y, then we will get 2 cos x cos 2y equal to cos of A plus B x plus 2y plus cos of A minus B x minus 2y. So using this concept, this cos x cos 2y is nothing but half of cos x plus 2y, half of cos x plus 2y plus half of cos x minus 2y. Okay, because here there is no 2. So multiply with half and divide with half. So half into in place of 2 cos x cos 2y, write this. So our differential equation is now d square minus dd dash of z is equal to half of cos x plus 2y plus half of cos x minus 2y. Now see, cos x plus 2y and cos x minus 2 both are of the form cos x plus 2y. So it comes under this model. Okay. Now let us start with the step 1. Step 1 deals with complementary function. It needs the knowledge of only LHS operator f dd dash. This d square minus dd dash only. Second step particularly deals with RHS function. Okay. So for step 1, we'll consider d square minus dd dash. Yes. So step 1. The auxiliary equation is, as per the procedure, what is the auxiliary equation? In place of d, we'll put m. In place of d dash, we'll put 1. So m square minus m into 1. So m square minus m equal to 0. That is our m square minus m into 1 equal. That is our auxiliary equation. So it can be easily factorized by taking out m as common. We will get m into m minus 1 equal to 0, which gives m equal to 0 and 1. Both are real and different. So m1, m2 are different. So our complementary function as per the procedure is given by some function f1 of y plus m1x means y plus 0x plus another function f2 of y plus m2x, y plus 1 into x. That is f1 of y plus 0x means f1 of y plus f2 of y plus 1x means y plus x. This is step number one, very simple. So we got the complementary function, some function of y plus some function of y plus x. Now coming to the second one, particular integral. As you know, particular integral means 1 by the LHS operator, 1 by d square minus dt dash. This is operate on the right hand side function. The right hand side function is already expressed as half of cos x plus 2y plus half of cos x minus 2y. Okay, we already simplified it using trigonometric relations. Since there are two terms, it is better to apply this 1 by f dt dash on both of them separately. So that means half of 1 by d square minus dt dash of cos x plus 2y plus half into this again 1 by d square minus dt dash of cos x minus 2y. Okay. So we have separated this as sum of two terms for our convenience, for making the calculations easier and to avoid confusion. We separate this as two terms. So let us name this equation as equation number 1. Now consider the first one. So consider the first one. Half of 1 by d square minus dd dash of cos x plus 2y. So what is the process? We have to replace d square with minus of a square and d dash with minus of ab. That is the process. Okay. So put d square equal to minus of a square. What is a here? A means quotient of x. So minus of 1 square means minus 1. And d dash with minus of ab. Here a is 1, b is 2. So minus of 1 into 2. So minus of 2. So put d square equal minus 1 and d dash equal minus 2. So then we will get half of 1 by d square is minus 1 minus of d dash minus of minus plus 2 of cos x plus 2y. So clearly denominator is minus 1 plus 2 means 1. It is non-zero. So half of 1 half of cos x plus 2y. See, very simple. By replacing d square with minus of a square and d dash with minus of ab, we got a non-zero denominator. So this first part is over. Now consider the second part. Half of 1 by d square d dash of cos x minus 2y. So now consider half of 1 by d square minus dd dash of cos x minus 2y. The second part of the particular integral. Here a equal to 1. So clearly here, what is a? Coefficient of x is 1 and b, the coefficient of y is minus 2. So as per the procedure, we have to replace d square with minus of a square, that is minus of 1 square, that is minus 1, and d dash with minus of ab. So minus of a1 and b minus 2 means 2. So put d square equal to minus 1 and d dash equal to 2. So then this particular integral becomes half of 1 by, in place of d square minus 1 minus in place of d dash 2 of cos x minus 2y. Now minus 1 minus 2 is minus 2, that is non-zero. So 1 by 2 into 1 by minus 3 is minus 1 by 6. So minus 1 by 6 of cos x minus 2. Okay. So for both the parts of the particular integral, we have calculated the value. Now, if you substitute these two values in our equation number 1. So by substituting in our equation 1, we get our particular integral is, what is our particular integral? Just go back once. This is half of this, the first one plus second one. The value of first one is half of cos x plus 2y, and the value of second one is minus 1 by 6 of cos x minus 2. Just now we calculate. So sum of those two will be our particular integral. So in place of first one, write half of cos x plus 2y. So half of cos x plus 2y, and the second part is minus 1 by 6 of cos of x minus 2y. So this is the particular integral. Now the last step, the complete solution. So the complete solution CS is the dependent variable z equal to Cf plus Pi. Z equal to Cf plus Pi. So z equal to Cf. Already we are calculating step number 1. It is f1 of y plus f2 of y plus x. So just write that. So f1 of y plus f2 of y plus x. And Pi, partial integral, is just now calculated. Half of cos of x plus 2y minus 1 by 6 of cos of x minus 2y. So where in the final answer we have to explain what is f1, what is f2. Simply write f1 and f2 are arbitrary functions. Arbitrary functions. For a second order PDE, the solution must contain either 2 arbitrary constants or 2 arbitrary functions. So here f1, f2 2 arbitrary functions. So this is the complete solution of the given problem. Okay. Now we will discuss one more problem, because in this first problem we obtained partial integral very easily. There is no failure case. Now we'll consider a problem where the particular integral will contain a failure case. Means we get 0 in the denominator by replacing d square with minus ab, d square with minus a square, and so on. So one such problem is there in our exercises. So let us take that problem. Yes. Solve dou cube z by dou x cube, dou cube z by dou x cube minus 4 into dou cube z by dou x square dou y plus 4 into dou cube z by dou x dou y square equal to 2 into sine of 3x plus 2y. Okay. Dou cube z by dou x cube minus 4 into dou cube z by dou x dou y plus 4 into dou cube z by dou x dou y square. Yes. First, express this equation notation form so that we can get the operator on the LHS clearly. Dou cube dou x cube. So in notation form. So in notation form, given PDE is same as dou cube by dou x cube means capital D cube object minus 4 times dou by dou x, dou square by dou x square into dou by dou y. Means capital D square into D dash. So D square into D dash object plus 4 times dou cube, dou by dou x, one derivative with respect to x, dou square by dou y square, two derivatives with respect to y. So D into D dash square object equal to 2 times sine of 3x plus 2y. So on the left hand side, the first term d cube is operating on z. The second term minus 4d square d dash is operating on z. The third term 4d d dash square is operating on z, yielding 2 times sine 3x plus 2y. So this is the given problem in the standard notation. Now, as for the procedure, what is step 1? We have to find the complementary function, and the complementary function depends only on the LHS operator. It has nothing to do with right hand side function. So for the complementary function, we need the auxiliary equation. The auxiliary equation is the equation obtained by simply replacing d with m and d dash with 1 on the left hand side operator. Okay. See, I'm not explaining why we have to replace d with m, d dash with 1. That is the interest of a science student. For engineering students, procedure is required. And after understanding this, we have to apply. So the auxiliary equation is m cube minus 4 times m square into 1 plus 4 times dm into d dash square 1 square equal to 0. Simply replace d with m and d dash with 1. So this is a cubic equation. Generally, for solving a cubic equation, first we have to apply trial and error method to identify boundary. But here, luckily, if you observe carefully, m is there in each and every term. So we can easily take out m as common. So after taking out m as common, you are getting m square minus 4m plus 4, a quadratic expression. So without the necessity of doing long division, simply we got product of one linear factor and product of one linear and quadratic factor. And the quadratic factor is also m square minus 4m plus 4 is nothing but m minus 2 whole square. So the roots are 0, 2, 2. Let us start with the equal roots. So 2, 2, 0. These are the three roots. M1, M2 are equal and M3 is different. So as per the procedure, so let us take 2 as M1, 2 as M2 and 0 as M3. So as per the procedure, the complement function is when M1 and M2 are equal, then correspond to M1, we will get some function of y1, M1x, and correspond to M2, which is equal to M1, we will get x into some function of same y plus M1x. In place of M2, we will write M1 and we will multiply with x so that these two cannot be combined. Plus third one, f3 of y plus M3x. Here M1 is 2, M2 is 2, M3 is 0. So we will get f1 of y plus 0x, simply y plus 2x. Sorry. So this is nothing but f1 of y plus 2x plus x into f2 of again y plus m1x means y plus 2x plus f3 of y plus m3. Since m3 is 0, we will get f3 of y plus 0x, simply f3 of 1. So this is our complementary function. Corresponding to the equal roots to m1, m2, we got the first two terms, and correspond to the third root 0, we got this third term. So this is step number 1. And step number 2 deals with the right hand side function. We have to apply the inverse operator of this d cube minus 4 d dash d square plus 4 d dash square on the right hand side function. So that is step number 2. So in step number 2, we will find the particular integral 1 by d cube minus 4 into d square d dash plus 4 into d dash square. Inverse operator of LHS to be applied on 2 sine. What is the problem here? Right hand function 2 sine of 3x plus 2y. 2 into sine of 3x plus 2y. Okay. Now, as per the procedure, we have to replace d square with minus of a square, d dash with minus of ab, and d dash square with minus of b square. That is the process. Okay. So what we'll do is, we'll consider first this as d square minus 4 into, what we'll do here, d square d dash. After taking out d as common, we can keep d dash. Here also after taking d dash as common, we can keep d dash. We can do like that. Or in place here, we can replace d square with minus of a square, and here d dash square with minus of b square. Whatever you like, we can do anything. So d square minus 4 times. Better to write this as d into d dash. Here also better to write this as 4d dash into d dash. Okay. Of 2 sine of 3x plus 2y. Okay. Now, put d square equal to minus of ab, minus of a square, minus of 3 square, minus 9. d dash with minus of ab. Minus of a means 3 and b means 2. So minus of 6. So we will get 1 by d square is minus 9 minus 4 into d of d dash minus 6 plus 4 into d dash into d dash minus 6. Okay. Is it okay? Of 2 sine 3x plus 2y. Okay. But here what we are getting is, we are getting one constant term, one d term, one d dash term. So it is not 0. And still d and d dash are present. So instead, we will do one thing. Alternatively, since we are getting d and d dash here and we are unable to get a constant answer here, what we'll do is, we'll do in another way. So alternatively, see, consider this again as 1 by d square here minus 4d square d dash. In this, what we'll do is, we'll simply take d as common. So leaving d dash. In the third one, Again, we'll consider this as 4d into d dash square. Just slight change, just observe carefully. In the third term, earlier we have considered dd dash into 4d dash, but here we have considered d dash square into 4d. Now, if you put d square equal to minus a square, that is minus 9, and d dash equal to minus ab, minus of 3 into 2, that is minus 6, and d dash square equal to minus of b square, minus of 2 square, minus 4. A is 3, b is 2. Then just see what happens. In place of d square, we will get minus 9. In place of d dash here, we will get minus 6. So minus 4 and minus 6 become plus 24d. And here 4d into, in place of d dash square, we will get minus of 4. Okay. So we will get, this is equal to 1 by, see what happens. In place of d square, I am getting minus 9. 1 by minus 9. Okay. Then minus 4d into dd dash. Minus 4d into minus 6. Minus 4d into minus 6. Plus 4d into d dash square. Plus 4d into minus 4. Plus 4d into minus 4 of 2 sine 3x plus 2. Okay. Now see what happens. 24d minus 16d is simply 8d. So minus 9 plus 8d of 2 sine 3x plus 2y. So denominator is not 0, but still d is there. So to get d square, as usual, just like in our LAD, we'll multiply and divide with 8d plus 9. So 8d plus 9 by 8d minus 9 into 8d plus 9 of 2 sine 3x plus 2y. Then we get 8d plus 9 of 8 into 8, 64d square minus 9 into 9, 81. Here we use the concept of a minus b into a plus b is a square minus b square of 2 sine 3x plus 2y. So now, as for the process, again we have to put d square equal minus of 3 square. So 8d plus 9 by 64 into d square minus 9 minus 81 of 2 sine 3x plus 2y. Now 64 into minus 9. 64 into 10 means 640. From 640, if we subtract 64, then we will get 586. So 64 into 9 minus 586. 9 into 4, 36. 6, 3, 9, 6, 54, 576. Sorry, 576 minus 576 minus 81 of 2 sine 3x plus 2y. And the numerator we have 8d plus 9, of course. Now, so this is nothing but 2 times 8d plus 9 by minus 576 minus 81. So 6 plus 1, 7. 5 plus 7 plus 8, 15. 5, 1, 6. So minus 657 of sine 3x plus 2y. Now, set this minus 67 outside, minus 657. So minus 2 by 657 into 8d plus 9 to be operated on sine 3x plus 2y. But what is d? Dou by dou x. So 8 into dou by dou x of sine 3x plus 2y plus 9 times this sine 3x plus 2y. Okay. Dou by dou x means partial derivative. The partial derivative of sine 3x plus 2 with respect to x is cos 3x plus 2y into again derivative of 3x plus 2y means 3. So we will get minus 2 by 657 into 8 times 8 into 3, 24 times cos 3x plus 2y plus 9 times sine 3x plus 2y. So this is our particular integral. So this is a lengthy problem. So we must be very careful while doing this. So first we have tried by taking d dash common in second term and third term. But with that, what happened? We got three terms, one constant term, one d term, and one d dash term. See here, we got 1 by minus 9 plus 24d minus 24d dash. So all the three terms remains. But instead of three terms, if we get two terms only, like a minus b, a plus b, then we can do easily. So instead of this, instead of doing like this, simply we have changed the strategy. So instead of this, from the second term 4d dash d square, we have taken ds common. From the third, we have taken, here also we have taken only ds common. And we have replaced d square with minus a square, d dash with minus ab, d dash square with minus b square. And we have got this. Okay, so the first step, complement function is over. Second step, paternity is over. So now we can declare the complete solution, step number 3. So the step number 3 is the complete solution is given by z equal to cf plus pi. That means z equal to some function of y plus 2x, f1 of y plus 2x. We already calculated this step number 1. Just go back and check. X into some function of y plus 2x plus f3 of y. This is what we are calculating step number 1. Okay. If you want, you can check once. Okay. So some function of y plus 2x plus x into f2 of y plus 2x plus f3 of y. And for particular integral, this minus 2 by 657 into 24 cos 3x plus 2y plus 9 sin 3x plus 2y. So minus 2 by 657 into 24 of cos 3x plus 2y plus 9 sin 3x plus 2y. So this is a bit lengthy problem. Intentionally, I have taken this problem so that I can understand difficult problems also. Okay. For more clarity, if you want, we can do one more problem also. So we will do one more problem for clarity because this is an important model. Okay. So we'll take only second order equation so that we can complete the problem very easily. Solve dou square z by dou x square plus dou square z by dou x dou y minus 6 into dou square z by dou y square equal to cos 2x plus y. So this is the last problem for this video. Since this is an important model, I have taken enough time, much time to explain this model. So directly we'll go to the notation form. So in notation form, the given differential equation is d square of z plus d dash of z minus 6 into d dash square of z, giving cos 2x plus y. Yes. Step number 1, the auxiliary equation is replace d with m. So first term becomes m square, second term becomes m into 1, third term becomes minus 6 into 1. So m square plus m minus 6 equal to 0, which after factorization becomes m plus 3 into m minus 2 equal to 0. That means m equal to minus 3 comma 2. Both are different. So our complementary function is simply some function of y plus minus 3x plus another function of y plus 2x. So direct, there is no confusion here. Now coming to the second one, that is the particular integral. This one, the inverse operator of this d square plus d dash minus 6 d dash square to be operated on cos 2x plus y. So step number 2, particular integral is 1 by d square plus d dash minus 6 d dash square to be operated on cos 2x plus y. Is it cos 2x plus y? Yes, cos 2x plus y only. Okay. Now, as per the procedure, put d square equal to minus of a square, minus of 2 square, minus 4, d dash with minus of ab, minus of 2 into 1, that is minus 2, and replace d dash square with minus of b square, minus of 1 square equal to minus 1. So then we will get 1 by, in place of d square, minus 4, in place of d dash, minus 2, minus 6 into, in place of d dash square, minus 6 of cos 2x plus y. But unfortunately here, we got minus 6 plus 6, 0. So we got a failure case. See, we are covering all the different types of problems that we can face in the examination. First one is direct problem. Second one is some bit complicated problem. Third one is a failure case problem. So it is a failure case. So what we'll do as per the procedure, we'll multiply with x, and in place of d square plus dd dash minus 6d square d dash square, we'll consider its partial derivative with respect to d. Okay. This is the process. Multiply outside with x and replace denominator with its partial derivative with respect to d. So we will get x into 1 by derivative of d square with respect to d, 2d. With respect to d dash constant, the derivative of d 1. So plus d dash. Okay. Then minus 6 d dash square. This comes simply 0. So cos of 2x plus 1. Okay. So derivative of d square is 2d. Derivative of d dash with respect to d is simply d dash. And this is entirely constant with respect to, because there is no d here. Now again, unless we get d square, d dash square, we cannot substitute. So as per the procedure, multiply with 2d minus d square and divide with same 2d minus d square. Already 2d plus d square is there in the 2d plus d dash is there in the denominator. Okay. So x into 2d minus d dash by a plus b into a square minus b square. So 4d square minus d dash square to be operated on cos 2x plus 1. Now again, as per procedure, we replace d square with minus of 2 square minus 4 and d dash square with minus of 1. So we get x into 2d minus d dash of 4 into, in place of d square, minus 4 minus of a square, and in place of d dash square, we'll get minus 1 to be operated on cos 2x plus 1. So 4 into 4, 16, minus 16 plus 1, minus 15. So x into minus 1 by 15 of 2d minus d dash of cos of 2x plus 1. Now apply d means dou by dou x, d dash means dou by dou y. So apply this on cos 2x plus. So minus x by 15 into 2d minus d dash. So 2 times d of cos 2x plus y minus d dash of cos 2x plus y. So 2 times d of cos 2x plus y minus d dash of cos 2x plus y. So after simplification, we'll get minus x by 15 into x times d means dou by dou x. So dou by dou x of cos 2x plus y minus d dash means dou by dou y of cos 2x plus y. So minus x by 15 into x into derivative of cos 2x plus y minus sin 2x plus y into derivative of 2x plus y with respect to x 2 minus dou by dou y of derivative of cos 2x plus y minus sin 2x plus y into dou by dou y of cos 2x plus y, simply 1. So minus x by 15 into 2 into minus into x minus 2x sin 2x plus y minus into minus plus into 1, 1. So plus sin 2x plus 1. Okay. So minus 2x plus 1 of sin 2x plus 1. So minus x by 15 into minus 2x minus 1, or x into 2x minus 1 by 15 of sin 2x plus 1. This is a particular integral. Now the last step is the complete solution. So the complete solution is given by z equal to CF plus PI. So z equal to CF. Already we calculated CF in step number 1. That is, what is that? F1 of 5 minus 3x plus F2 of 5 plus 2x. So F1 of y minus 3x plus f2 of y plus 2x. This is complex function plus particular integral plus x into 2x square minus x into 1x by 15 of sine of 2x plus. So this is the complete solution of the given problem. So in this particular video, we are concentrated on method of solving PDEs of this form. F of d dash of z equals sin ax plus by plus cos ax plus by. Just a brief summary. As per the procedure, the complement function is as usual, the same in all the models. And whenever the right hand side function is the sine or cos x plus by, then finding the particular integral, what we'll do is, in the given f of d dash, we'll consider only d square term, d dash term, and d dash square terms. We'll replace d square with minus of a square, where a is the coefficient of x. We'll replace d dash with minus of b square, minus of ab, and d dash square with minus of b square. Then the denominator, if that is not equal to 0, then we'll stop the complement function, the particular integral there itself. If the denominator becomes 0, then replace the denominator with derivative with respect to the partial derivative with respect to d and multiply outside with x. Still, if the denominator becomes 0 after replace d square with minus a square, d dash with minus ab, d dash square with minus b square, then multiply with 1 more x, replace denominator with second partial with respect to d, and then apply the same process. This is the method of finding particular integral. And the last step, declare the solution as z equals cf plus va. Okay. So, in the next video, we'll discuss the method of solving f of d dash of z equals some algebra function of x and y. That will be our video number 4. Okay. So, practice some more problems based on this.